order to get through that. That's why I mentioned there's a little bit of physics in terms of just remembering your whole relationship between energy and wavelength and stuff. But chemistry does mention that as well. So let's go on to the next question here. So, as our next question, we have lead thiocyanate, PbSCN2, SCN2, has a KSP value. Okay, so I had to actually search this one up because there's not weird values there, but it's actually 2.00 times 10 to the negative 5. Okay, that's what that's trying to say. That's what we have for lead thiocyanate. Part A is telling us to calculate molar solubility. So in a sense, how much in pure water will this dissolve? So remember the K value is pretty much saying how much dissociates and how much dissolves. So using that, we're just going to find a value that represents how much of lead thiocyanate solid when put into water would actually dissociate. And the way we do that is by using the formula known as this. So KSP is equal to, actually, before we even do that, let's just move this down here for some space. First, what we need to do is see what that lead thiocyanate breaks down into. So this is what the formula would look like. We have PbSCN2 solid, okay? And when quote unquote thrown in water, in pure water, okay, it's a equation that goes back and forth. We have Pb2 plus aqueous plus SC2SCN minus aqueous. Okay, so that means, remember that the KSP is the moles of, moles per liter of product over moles per liter of reactants, but only if they're aqueous solutions, so we don't count the solids. So in a sense, what we really have here is Pb2 plus, okay, and SCN minus. Now you're probably wondering right away, how do we reflect the 2? When it comes to the K value, what happens, right, is that when you want to reflect that 2 in front of it, you square it. So this is going to be our KSP formula that we're going to be using. And here we also need an ice table. So initial, change, and equilibrium. So we don't really know how much we started with, but in this case, it doesn't really matter because we're only focusing on the aqueous solutions being produced, because this is how we find our molar solubility. So we have that there's going to be, it starts off with 0, and the change is going to be plus x, same here, well actually plus 2x, because whenever this loses, so let's just say it's a value like a, because based on this form we don't need it. So initial is a for the PbSCN2, okay? So the way it translates, just use a different color. This matches up with there, this matches up with this, and this matches up with that. So for every 1 A loses, X gains 1, the Pb, and the SCN gains twice of that, based on this formula here. So we have just A minus X is a change, it's going to be X, and this is going to be 2X. Okay, so that means that really the KSP for this one here, if you just plug it in, it's going to be X times 2X squared. So KSP is equal to 4, because it's going to be squared, and instead of X squared, because it's an extra X, it'll be 4X cubed. So now let's just plug it in. That means that the 2.00 times 10 to the negative 5 is going to be divided by 4. Okay, that's going to give us, x cubed. So all of this is going to be cubed. I mean, the opposite of that. All right, so this is what we have here for that step. Just so we're keeping along. Just going to move this over to the side. Okay. So that's what we have there. And we find out that when we do that, X is equal to, let me just double check here, the calculator, 1.71 times 10 to the negative 2 moles per liter. And this right here, this X value, is going to be our molar solubility for this question. So it pretty much means for whatever value of A that's put in, that's how much is going to be produced in pure water. Now, they're asking us what happens now if it's not pure water. What happens if we actually have 0.900 moles per liter of PbSCN. Now, fun fact, most things, in fact, if not all, when it's a solid that's with potassium, and especially in these questions where they don't mention that it has a K value, you can just assume they dissociate completely. So if we wrote down the formula, PbSCN, it'd just be an arrow going one way, K plus, aqueous again, because this is solid, plus SCN minus aqueous. This is what it turns into. So if we know that we start off with 0.900 moles per liter of PbSCN, it means that we have 0.900 moles per liter of K that's produced and 0.900 moles per liter of SCN minus. The only one that's important here, based on the formula above, the PbSCN2, you guessed it, would just be the thiocyanate, this part right here. So now if we go back to our ice table, it'll look relatively similar, but the difference is that our initial now will no longer be 0 for that part. So if we just put A again, 0 for the lead part, okay? And then here, instead of it being 0, it's going to be 0.900. And that's a huge amount in terms of the moles, okay? And the reason why I say that's a huge amount, because that is going to play into what we have to do with the later steps, okay? So the change here is going to be, again, plus X minus X, and here's 0.900 minus 2X, okay? And here again, this one is not relevant. We don't really need this part. This one's still going to be X. Now here is where it matters. You can see in our last question, what we really got here in this theoretical X was 0.0171. This is going against the 0.900, okay, theoretically. That doesn't stand a chance. Like the amount, whoops, it's not even going to be minus, it's going to be plus. Sorry about that. The amount that's going to be added to the 0.900 is almost going to be so insignificant that in the end, we're really just going to have 0.900 still. Because the fact that there's so much thiocyanate and because the K value is so low, it's not really going to change how much thiocyanate we end up with. And that right there is going to help us solve this question, because what we really have now in this question is the KSP is equal to X times 0.900 squared. Okay, so X in this case is just going to be the KSP over that 0.900 squared. And you'll find when you plug it into the calculator, as you can see, the X produced is really small, 2.47 times 10 to the negative 5 moles per liter. And this right here would be the molar solubility when there's already some product there, in this case, in the thiocyanate. Now the rule of thumb, and most questions, if in fact not all, would have to do this, or else you would end up with a trigonometry type of equation, like something to the cubed, and you don't want to work with that. It's very frustrating. I tried it. When you have a starting amount that is more than 1,000 times bigger than your K value, in this case it's 2 to the negative 5, and this is really just 9 to the negative 1, that's already 1,000 times bigger. You can just kind of ignore it and say that the change here that we saw is negligible. Hence why we could go ahead and do this step here. Okay, so that would be the answer to that question here. Let's see how they did it. Okay, yep, 1.71 times 10 to the negative 2. Perfect. And here, yep, they did 2x 900 and then they actually did try to go with doing the cubic equation. They definitely have to show me how to do that. But overall, they should have gone exactly that. It would be 2.47 times 10 to the negative 5. But the key here, personally to me, is that the 0.900 doesn't change much, which is why you can just solve it like that, okay? Alright, now on to the next question.